Whenever we're doing any calculations related to science, we come up to the problem of significant figures. But what are significant figures? And how can I know how many significant figures do I have? And why do I have to focus so much on significant figures? Are they that important? And why? All of this is going to be in today's video. But first, Assalamu alaikum. Welcome to my channel, Phi and Maths with an S. Yes, the S is intentional, providing physics and math tutorials for secondary level and beyond. Make sure to subscribe and to easily find all lessons and write down any requests in the comment sections. Now going back to our topic, significant figures are strongly related to measurement. Significant figures actually decide the whole accuracy of my measurement, whether I'm doing an experiment or I'm just doing a simple measurement, or even if I'm just solving a problem. We know that because we are humans, we make mistakes. There is no measurement that is 100% accurate. And so, because of that, I have to always be aware of my margin of error. And to talk about the margin of error, we have a simple example here. Let's say that this is a ruler, and those numbers of in the ruler are centimeters. So here I have 1 centimeter, 2 centimeters, 3 centimeters, 4 centimeters, 5 centimeters. If I want to measure the length of any object, I simply put it next to the ruler like this and see how long is the object. Now here we can notice that the object is slightly above 3 centimeters tall. So what to do? Instead of telling you what to do, let's see what we should not do. What we should not do is make an estimation, like saying this is 3 and 1 over 4 centimeters tall, or 3.5. Why so? Because this ruler has only centimeters. It doesn't have half centimeters or third centimeters. So I should stick to the smallest unit of measurement. However, I should write my uncertainty because I'm uncertain if it's 3 or something above 3. So I should write my uncertainty by saying that it's 3 centimeters plus or minus the smallest unit of measurement here. So the smallest unit of measurement here is 1 centimeter, so it's plus or minus 1 centimeters. And it's actually written like this: 3 plus or minus 1 centimeters. There are different notations, but we're not focusing here on the notation, we're just focusing on the concept. So what does this mean? This means the length of this object is 3 centimeters, but if I have made any error in my measurement, the error is only going to be off by 1 centimeter. So it can be 3 centimeters, it can be 2 centimeters, and it can be 4 centimeters. But it cannot be 5 and it cannot be 1 because my margin of error is plus or minus 1 centimeter. Now this is a huge margin of error, but this is so huge because I'm actually using a ruler that doesn't have millimeters. So if I have a ruler that actually has millimeters, okay, I have added millimeters to my ruler, and now we can say that it's 3.12, let's just make it 3 here. So it's now 3.3 millimeters, centimeters, sorry. So now I can say that it's 3.3 centimeters. Now here I am more certain than in the previous measurement. In the previous measurement, I know it's 3, but it can be plus or minus 1 centimeter. Here I can say with more certainty that it's actually 3.3 centimeters. But again, nothing is 100% accurate. So again, I'm going to have to write my margin of error. Like, what is my margin of error here? Again, the margin of error is going to be equaling to the smallest measuring unit I have. So it's going to be plus or minus 1 millimeter or 0.1 centimeters. Now, what is the difference between this and this? It's actually a huge difference. In this here, if I made an error, I can say that it's either 2 or 3 or 4 because it's 3 plus or minus 1 centimeters. But here, if my margin of error is significantly smaller, it can be 3.3, can be 3.2 or 3.1 centimeters. Now, the margin of error here is drastically smaller. Why? Simply because I have a more accurate measuring device. Whenever you're using any kind of measuring device, the smaller the units that you have in the measuring device, the more accurate is your measurement and the smaller is your margin of error. And if the smallest unit in that measuring device is a big unit, then you're going to have a huge margin of error and you're going to have so much uncertainty. And this uncertainty is expressed using significant figures. So how can we use significant figures to explain uncertainty? If we look here again in those two measurements, in the first one, I can say that this is 3 centimeters. I cannot say that this is 3.0 centimeters. Here comes significant figures. In the second one, even if it was really 3, like let's say that it actually ends on 3 here. In the second measurement here, because I have millimeters, I can say that it's 3.0 centimeters and I cannot say that it's just 3 centimeters. Using significant figures, the first thing you do when you look is you know the smallest unit of measurement and then you know your uncertainty. Like, significant figures have rules. But before we go to that, let's just expand on this. If I have something that is said that is it's 3.0 centimeters, then I know that the smallest unit in this measurement is 0.1 centimeters, which is a millimeter. But if I have just 3 like this, then I know that the smallest unit is 1 centimeter. If I have a measurement that is written like this, 300 centimeters, then I know that the smallest unit of measurement in this device is 0.01 centimeters, and so on. Like, we can use this now to know the rules of significant figures. Number 1, all non-zeros are significant. All non-zeros are significant figures. For example, 135 has 3 significant figures. And 2.355 has 1, 2, 3, 4 significant figures. And so this is the first rule. Any number that is not a zero is counted as a significant figure. Type number two, zeros to the left of numbers, of non-zero numbers, are not significant figures. For example, 135 has three significant figures. We said that 135 has three significant figures. If I have a zero here or a zero here, it still has three significant figures because those zeros are to the left and so they do not count. If I have 0.006, this has only one significant figure because zeros to the left, again, they do not count. So here I still have one significant figure. Right. Rule number three, zeros between numbers, and by numbers I mean non-zero numbers. I just don't write it to save time, but zeros between non-zero numbers are significant figures. For example, 103004. This number has 1, 2, 3, 4, 5, 6 significant figures. Now those zeros here, I can count them as significant figures because they are between numbers. Not like this. Here they are not between numbers. Here they're just to the left. And the final rule, zeros to the right are significant figures in one case, if the number has a decimal point. What do I mean? If I have 50, now this is a zero to the right. Is it a significant figure? No. Why? Because 50 here has no decimal points, and so here I have only one significant figure. But if I have 50.0, now this number here has a decimal point, so now I can count the zeros and the number now has three significant figures, which is 1, 2, and 3. Again, I can count the zeros now because there is a decimal point. And those are all the rules for significant figures. They're actually not very complicated. They're pretty simple and they are straightforward. And using those rules, you can calculate how many significant figures you have, so you can use that in your calculations and in your problems. Okay. Using significant figures. We have already covered the first part of using significant figures, which is my measurement. If I have a measurement, I will have to write the measurement with decimal points in a number of significant figures that are correspondent to the accuracy of my measurement, or to the number to the smallest unit of measurement I have in my measuring device, whether it was a ruler, whether it was a time machine, like not a time machine, like a clock or watch or stopwatch, whether you're using measuring cylinder for liquids, and so on. Now, the other part of using significant figures, which is the one that we focus on more, is after we took our measurements, when we were doing our calculations, when we were doing an experiment, you actually use different measuring devices for different things. And so you're going to have different accuracies or different errors of margin. And evidently, you're going to have to use numbers with a different number of significant figures. And so, how are we going to do so? And even if we're not doing the measurement ourselves, if we're doing a problem, if we're solving a problem, the problem is provided with different numbers that have different significant figures or different number of significant figures. And how are we going to do so so we can make our answer as accurate as possible? The first thing is when we are multiplying. First of all, before we even go into multiplying and adding and subtracting and whatever, we always try to match the accuracy of the measuring device in our final answers. So if I am giving a problem, if I am given a problem, my final answer to this problem has to correspond to the accuracy of the given numbers in the problem itself. I cannot add accuracy. For example, if I am given an accuracy of 3.0 centimeters, I cannot have an answer that has more accuracy than this, or even less accuracy than this. So I try to match the accuracy. How am I going to do so? So if I am multiplying different numbers with different significant figures, for example, let's say that I have 3.1416 multiplied by 2.34 multiplied by again 0.58. Now those are three different numbers and each one of them has a different value for significant figures. Whenever I'm multiplying and dividing, my final answer should match the least number of significant figures. Now here in the first number, I have 1, 2, 3, 4, 5, 6, sorry, 1, 2, 3, 4, 5 significant figures. Here I have 1, 2, 3 significant figures. But in the last one, I have only 2 significant figures. So when I give my answer, of course, when I put this in the calculator, I'm going to have a number with a large number after the decimal point, but I have to round it up to two decimal places here, or not two decimal places, but I have to round it up to a number that has only 2 significant figures, which is the least in the given problem. So the final answer is going to be 4.3, only 2 significant figures. I don't remember actually the real number that I get, but let's say that it's 4.2987, something like this. I have to round this up to just 4.3, which is 2 significant figures as this one. If I have division, let's say I have 0.75 or 745 multiplied by 2.2, and all of this is divided by 3.885. Now here again, I'm going to do the same thing. I'm going to find the number that has the least significant figures, which is this one, evidently here, 2 significant figures. So my final answer should have only 2 significant figures. So I'm going to round up the final answer to 0.42, which has only 2 significant figures. Now pay attention here. This 0 here is not counted because it's to the left, although the number has a decimal point, but it's still a 0 to the left, and all zeros to the left are not significant figures. If there was a number here before it, then we can count it, but as long as there is nothing to the left of this zero, then it cannot be counted as a significant figure. Type. What if I have a number that has a power of 10? For example, 1.3257 multiplied by 10 to the power of 7 multiplied by 4.11 multiplied by 10 to the power of negative 3. Now again, I'm going to have to do the same thing. I have here two numbers, and I have to find the number of significant figures in each one. This one obviously has more significant figures than this one, and this one has only 3 significant figures. So my final answer should be a number that has only 3 significant figures, which is 5.45 multiplied by 10 to the power of 4. Now, if I say that it's 54.5 multiplied by 10 to the power of 3, it's possible. As long as I have 3 significant figures, there is no problem. The problem is when I change the number so it has more or less than 3 significant figures. So we focus on the number of significant figures, because a lot of times people get confused on, should I write it like 10 to the power of 3 or 10 to the power of 4, which has its own rules that we can talk about in a different video. But here in significant figures, all we care about is that the number itself has 3 significant figures. Now we go to the sum, adding and subtracting numbers with significant figures. Now, when we're adding and subtracting numbers with significant figures, we do not focus on the number of significant figures themselves. What we focus on is the decimal place. For example, if I have 123.62 plus 8.9, now here what I focus on is the number of decimal places. Here I have 2 decimal places, but here I have only 1 decimal place. So my answer is going to be a number that has 1 decimal place, which is 123.5. So 1 decimal place as well. Another example, I have 27.153 plus 138.2 minus 11.74. Again, the least number of decimal places is here, which is only 1 decimal place. So my final answer is going to have only 1 decimal place, which is 153.6. And this is all about how to multiply, divide, add, or subtract numbers that have significant figures, or when I'm paying attention to significant figures. Now, here's a big question. When am I supposed to round up? If I am doing a problem, when am I supposed to round up to the number of needed significant figures so it cannot be more or less? If you have to do so many calculations on one problem, let's say that you do calculation A and then use the number in calculation A in calculation B, and then use that number again in another calculation, and so on until you reach your final answer. So you have to do your problem on many steps. Here, you should not round up your numbers on each calculation, because when you're rounding up so many times, you're going to get a final answer that is not very accurate. For example, you round up the first number and then you use this in a different calculation and you get an answer and you round up this number again, and then you're going to use it in a different calculations. When you get to the final answer, you're going to have the final answer is going to be so much affected by the numbers that you have rounded up 2, 3, or 4 times. So whenever you're doing a problem or a calculation that has many steps, you should not round up until you reach the final answer. So for each calculation, you're going to need to use the full number. You can save it on your calculator, or you can just write it down. Anyways, you should not round up the number and use it in its long form as it is. Once you get to the final answer, then instead of writing it in a long form, you have to round it up to the number of significant figures you are supposed to do. For example, if you're supposed to round it up to, let's say, 5 significant figures, then 1, 2, 3, 4, 5, you stop here and you round this for up to 5. So you're only going to round up when you reach your final answer. But if you're provided with a simple problem that has only one calculation, then you're just going to round up right away because eventually it's your final answer. So in any ways, you should only round up in your final answer. If you have a simple calculation, then you are already at your final answer. And if you have a more complex calculation, then you have to wait until you get to the final answer and then to round up to the number of significant units you need. Let's have an example of this. If I have a laser light that took time, I'm just going to try to write a short form of the question. Let's say it took 176 multiplied by 10 to the power of negative 6 seconds. I want to find the distance. Given that the speed of light is not 3 multiplied by 10 to the power of 8, no, it's 2.9989, sorry, 792458 multiplied by 10 to the power of 8 meters per second. Now, whenever you're given a problem, you are given different numbers, you're going to look for the smallest number of significant figures and match your final answer to that. Now here, the smallest number of significant figures here is 1.176. We are given the speed of light in a high accuracy, so I'm going to follow this one. So whenever I'm doing the answer, we know that distance or speed equals distance over time, and so distance equals speed multiplied by time, and so the distance covered by the laser light is going to equal 1.176 multiplied by 10 to the power of negative 6 seconds multiplied by the speed of light, which is 2.9979245 multiplied by 10 to the power of 8 meters per seconds. Seconds divided by seconds equals 1. And when we put those numbers in the calculator, I'm going to get a huge number that is 352 multiplied by 555,936 meters. This is what I'm going to find in the calculator, but this is not going to be my final answer. My final answer should match the number of significant figures here. So I have 1, 2, 3, 4 significant figures. So my final answer should be 4 significant figures only. So 3, 5, 2.5 meters. Actually, this 5 is rounded up to 6. 352.6 meters. Now again, my final answer should always match the least number of significant figures given in the measurements in the problem. Now, let us say that the speed of light given in the problem is just 3 multiplied by 10 to the power of 8, not this humongous number. Is this going to affect my final answer? Yes. Now, I have a smaller number of significant figures here in this measurement, which is only one significant figure. So my final answer here is going to be 3 meters instead of instead of 352.6 meters. My final answer should contain only one significant figure, which is going to be 300 meters. Notice by how much the accuracy dropped here. The accuracy changed so much because I just changed the number of significant figures I have here. You can say 300 meters, or you can say 3 multiplied by 10 to the power of 2 meters, which is practically the same. But anyways, I have only here one significant figures. These zeros do not count. They are to the right, but there is no decimal point, so they cannot be counted. And so the answer changed because the measurement here changed. The accuracy of the measurement changed, so the accuracy of the answer changed. Now, again, this is very important. Uncertainty is very important. Noting down the exact accuracy of your measurement is very important because whenever you're doing a real experiment, a real scientific experiment, the accuracy changes everything in the experiment. So your uncertainty is very important. It can change a huge deal of your results in an experiment just because of your margin of error or because of your uncertainty. Now here, because I'm just focusing on the significant figures part, not the uncertainty part, I did not write in all of the previous problems the margin of error, but remember that we always have to, by the end, have a final margin of error, which is, in this case here, just by looking at the number, it's 0.1 meters. While here, just by looking at this number, it's plus or minus 1 meter. You see how much the accuracy changed? By the way, just for a disclaimer here, this is not actually how we do the margin of error. We actually take the margin of error from the rule itself, but I just here wrote a margin of error depending on the number itself, not depending on the whole problem, just to show the difference in the uncertainty or in the margin of error between those two numbers. That would be it for this lesson. I hope that it was enjoyable and educational. Don't forget to share and subscribe, and write down in the comment section any requests you have for any problems that you want me to solve or any topic that you want me to include in the future videos. Thank you.